Gennady, many thanks for inviting me. This talk is about an operator and a half line, and all functions are scalar valued, so no matrices. Sorry about that. And don't worry about Levy processes if you are not comfortable with probability theory. Neither am I. Probability will be very much in the background. And it's there just to motivate. You see, the operator that I will be looking at is a very, very particular model operator, and I just use probability background to explain why we're interested in this particular operator. So if you are not interested in motivation, you don't need to listen to probably the first 2/3 of my talk. Okay, so relax. Now, this is a joint work with Tony Hill, who was my PhD student, and the main results are in his PhD thesis, which you can see on arXiv. Unfortunately, we have not still published them, so although the results are not very new, they are not very known either. Gennady knows them because he was an examiner, and Tony participated in the program 5 years ago, and many people have been asking about him, and I just feel like saying a few words about him, although I know he would have hated this, but he's not here, and he doesn't need to know about this. So this was Tony's second PhD, and actually Tony is probably one of the most amazing and inspirational people I have ever met in my life. So he did his undergraduate degree at Oxford some years ago, and although he was mostly interested in pure maths, he somehow ended up doing a PhD elsewhere in engineering maths. And then, I think he was a teacher in the 1970s, and then he switched to a career in software industry, and he became a chief executive officer of Micro Focus, and then he was instrumental in floating this company in London Stock Exchange, 2005, and I think at some point he was voted the best CEO in this country. And then he took an early retirement, and actually, and then he decided to come back to his first love, pure maths, and then he decided to pursue another PhD in maths. But before that, you see, because he had a very long gap in his academic career, he decided to kind of check whether he was still capable of doing maths. And so he did a master's degree at Open University. So Open University, for those who are not from this country, it's kind of distant learning. And his MSc, obviously it was a distinction, and I think it was in high 90s. So, and then he came to King's and he did a PhD, but he does a lot of charity, and I show you on the next page is what exactly he has been up to lately. But his background, you see, he was, oops, no, this is not what I meant. So he was the first in his family to go to university. And so I'll talk about charities shortly, but basically, so he's a long distance runner and walker. Now in 2014, he became a centurion, so means walking 100 miles in 24 hours. And I think he did it, he was in his 60s, and he kind of tried 2 years earlier and failed. And then, I don't think at that age your physical ability necessarily improves with age, but in his case, it did, and so he managed to do this. And by the way, long distance running, for those who don't know what it is, if you're thinking about marathon, you're wrong. Marathon is 26.2 miles, and Tony does 100 miles. So it's like, imagine 4 marathons. So this is what he does, maybe still. Okay, and so about so these days he mostly does charity, and this is, I think he created this leveling up STEM, so science, technology, engineering, maths program. And so basically they're helping people from underprivileged backgrounds to go to uni. And so they started in 2021. And they it's maths, they provide tuition maths, physics, chemistry, and they started at, was it 4 universities, and now this year program involves 750 kids, and total 21 universities, and they are looking at increasing the number of students. And, well, so this is what London Math Society had to say about him. This is from their webpage. So London Math Society is involved in this scheme, and a similar one from the Institute of Physics. So basically, for him, it's like a full-time job now. He runs the charity and he puts his own money there. So, but at the end of the talk, we'll talk about his maths, and I will show you why I'm so excited about this. Okay, so now let me switch to maths. Basically, I will start. Eventually, my operator will be on half line, but somehow I try to motivate this by a multi-dimensional case. So suppose we have this fraction Laplacian, so you have the Fourier transform, then you multiply by the modulus of psi to the power 2 alpha, and then you take the inverse Fourier transform if alpha is 1, so this is just the Laplacian. And this restriction it comes from probability theory, so yes, they're interested in this case. And so, well, you can write the corresponding sesquilinear form, so this particular formula is not important for me in Rn, but very often in the probability theory they operate in terms of Dirichlet forms, so this will be a little bit more relevant a little bit later. So, and so this is the generator of a Levy stable Levy process, and kind of the theory is more or less well understood in the case of Rn. And, well, the natural thing is that suppose we have a domain, suppose the process is not in the whole of Rn, but in some domain, you can, at this point, you can assume that the boundaries are infinity smooth, and suppose because we'll have this operator, there will be some function spaces in the background. You can think in terms of Sobolev spaces. It doesn't matter. So what matters to me is that because we are restricted to a domain, so there will be two operators. One is the operator of restriction from Rn to the domain. And so if you take the function space on the whole of Rn and restrict it to the domain, so this is the notation for this. And another operator is, suppose I have functions on the domain, and I would like to extend them to the whole of Rn, I extend by 0. Kind of the natural thing to do is to extend by 0. And so I guess the natural thing, so the fractional Laplacian is this. So you take a function that is on your domain, you extend it by 0. I mean, because the fractional Laplacian involves Fourier transform, and for Fourier transform, you need to know the function on the whole of Rn. That's why you're extending it to the whole of Rn, and extending it by 0 is a natural thing to do. And then you restrict it back to the domain. So this is a fractional Laplacian on the domain. However, when you do this, you are creating a problem. Because if your function u was not 0 at the boundary, when you extend it by 0 outside the domain, you create a jump. And because you have now a pseudo-differential operator, think of when you have a Laplacian, you will have just a differential operator. So you're differentiating a discontinuous function, so you are creating a singularity. And so what may happen is that, well, if u was not 0 at the boundary, then extending it by 0 creates a discontinuity. So this might have a singularity, And then your operator might not be a sort of well-defined bounded operator in the spaces, even if the corresponding operator on the whole space, on the whole of Rn, was fine. So just because you created the singularity at the boundary. By the way, for differential operators, we don't need, they're local, and this is a pseudo-differential operator. It's not local. So for pseudo-differential operator, we don't have choice. You need to apply the Fourier transform, so you need to have it, the function of the whole of Rn. For differential operators, you don't need to do this. It's everything local. But suppose we do this. So why don't we have this difficulty? You see, what happens is that when you, if this, had this been a differential operator, this would have had delta function-like singularities at the boundary. You restrict that to the domain, they're lost. And that's why we don't have this difficulty for differential operators. Now, when you have a pseudo-differential operator like this one, it's not a delta function. It's not a sharp singularity. It will be a power-like singularity. And so let me show you an example. So one-dimensional example, half line. So suppose we have alpha between 1/2 and 1. And suppose we have a function, I don't know, the best function in the world. So the function is constant 1 on the interval from 0 to 1. And then it kind of goes C infinity smooth from this value 1 to the value 0. Kind of smooth stack, if you like. This is a compactly supported, C infinity smooth. And suppose I kind of see what happens here. And so it's a very simple calculation. I don't need to kind of waste your effort on this. But one thing is kind of what I alluded to. So when you stand by 0, you remember the function was 1 to the right of the origin. And if I extend it by 0, so when I differentiate, I have a delta function. If I have a differential operator, then when I restrict everything back to the domain, this delta function will be lost. But now, because we have this non-local term, what you end up with is a power. And you cannot get rid of that. And so the punchline is that we had a C infinity smooth function. We apply this operator, and the result is not even integrable. And because of difficulties of that kind, the theory of there is a theory of boundary value problems for elliptic pseudo-differential operators, but unfortunately it does not answer the questions that people in probability theory have. And there are and the difficulties are related to this. There is a theory due to Boutet de Manuel, which does not apply to this operator at all, because there is a so-called transmission condition that is not satisfied for the fractional Laplacian, and actually it is not satisfied for any generator of a kind of stochastic process, more or less. And there is a theory by Wyszek and Eskin. But there you have to assume that functions are 0 at the boundary, and therefore only the Dirichlet problem is okay, and nothing else that is of interest to people in probability theory can be derived from that. Now, the Dirichlet problem, this is a very well-known thing going back to Marcel Ries in 1938, that the Dirichlet problem for the fractional Laplacian is where you have the boundary condition not at the boundary, but in the complement of the domain. It's a very well-known thing that this is so-called balayage boundary condition, Dirichlet boundary condition, that it's the whole complement of the domain rather than at the boundary. And there is a kind of very nice intuitive explanation of this from the probability theory point of view, because when we have the Laplacian, the corresponding process is Brownian motion that has continuous trajectories. For a particle moving according to Brownian motion, to get outside the domain, it needs to cross the boundary. And kind of everything is fine. The Levy processes governed by fractional Laplacian, they have jumps. And they're particle can leave the domain without crossing the boundary, just jump outside. That's why in kind of from the probability point of view, risk condition, so the risk boundary value problem, so the balayage boundary value problem, Dirichlet problem, involves the function complement of the domain. Anyway, right, so, but people in probability do stuff, and what exactly are they doing? Well, so, again, so suppose you start with the sesquilinear form, it looks familiar, but now remember there, on one of my kind of first pages I had Rn here, now you just restrict to the domain. If you look at the corresponding operator,
minus is missing, right? Because this quadratic can be
oh,
anyway, right?
this missing, and I thought I uploaded a new file. I noticed that before my talk. I corrected it, and I thought I uploaded the file, correct file there. But you're absolutely right, should be minus here. Yeah, absolutely. Yeah, yeah. So this is, and the corresponding operator is this. And this is almost the fractional Laplacian that I showed you. Not quite. It also has a potential. So a potential is given here, and you can see that now the integration is over the complement of the domain, and x is in the domain. So x and y, they don't meet, the integral exists, but what happens here is that as x approaches the boundary of domain, it gets close to y's, and therefore the potential grows at the boundary. Okay, so it's a singular potential. And so people were trying to kind of, from the analysis point of view, people were trying to help people in probability, although people in probability don't need help of analysts, but kind of our ambition is to kind of get involved. And so you can see that this operator, it looks like the standard Schrödinger operator. So in Schrödinger operator, you have the Laplacian plus a potential. Here you have the fractional Laplacian and the potential. And kind of the logic is that, well, so Schrödinger operator is a sort of a perturbation of the Laplacian. So this fractional, sort of regional fractional Laplacian should be treated the same way. And if you kind of apply this logic, so you start with a boundary value problem for the fractional Laplacian. And I told you there are difficulties with that. And we cannot do what probability people are interested in. And then, well, suppose you manage to do something about it, and then you hope to deal with the singular potential. Kind of the natural thing if you think of the Schrödinger operator. And it doesn't work. And now what happens here is that, let me go back to this one-dimensional example. So we know that if you apply this fractional Laplacian to a good function, in general, you have this singularity at 0. Now, if you do the calculation for this potential, singular potential, you notice that it also has a singularity of the same order. And what happens is that when you actually consider this operator, the regional Laplacian, then they cancel out. And it's not just kind of really miracle, because if you do sort of, so the punchline is that you do not, so you do not treat, so you do not treat this as a perturbation of the fractional Laplacian. This combination is an unperturbed operator. This is the original operator, and what happens is that both of these terms are more singular than their sum. There's a cancellation there. So therefore, one needs to treat this as the original operator. And if you kind of change the coefficient in front of this here, the whole thing is ruined. It's a different operator, and it's much more singular. So therefore, the reason kind of, I think I will rush you through this. Basically, it's very easy to see that you can rewrite this potential as the fractional Laplacian applied to the indicator function, characteristic function of the complement of the domain. And it's, so this is your operator. And so in general, if it's not just fractional Laplacian, it turns out that if you have any more or less pseudo-differential operator, and you look at this combination, it's actually a better operator than just this. And this is the right thing to look at. And there is a kind of explanation. I don't have time for this, but just wanted to flash this at you because it's a simple calculation, and at some point you have a commutator which is usually lower order than the original operator, and that's why this operator is a better thing. So, okay, so that was kind of an introduction. One more technical slide, spaces. I will need basic potential spaces. Again, so just a sec. So suppose this is an integer, then you can see that this is simply Sobolev space. And so for non-integers, so this is kind of Sobolev space of fractional order. We have the same notation as before. And one more thing, when S is greater than 1 over 1 plus P, so we will have this space with 0, and this means that the derivative is 0. But it's important that we not require that the function is 0. This is of utmost importance. So basically, kind of we don't have Dirichlet condition, but we have the Neumann condition in a sense. And this is exactly what was needed there. And look, I will come back. How much time do I have? I started late, I think.
Yes, you did. Well, in the timetable says 12:45, but I guess we can extend a bit.
Okay, so at this moment, this is just a sort of transcendental equation. So this equation, I will come back to this. So this equation for alpha, alpha is the order between 0 and 1/2 doesn't have solutions between 0 and 1, and between 1 and 2 for any alpha it has just one solution that is between 0 and alpha. And the main result is stated so this is the equation that I mentioned. It's not quite Laplacian, it's 1D. It's not quite Laplacian, we did 1, it's kind of standard thing. This is an easy operator. And so the main theorems are that the operator in this regime is bounded invertible, but I guess this case is more interested when we go above 1 plus 1 or P's. This is more interested to people in probability, I suppose. And there, remember that root of the transcendental equation. And so up to that root, the operator is bounded and invertible. And above, it has a trivial kernel and has Fredholm index -1. So these are the main results. But what I wanted to show you, and I will do this very, very quickly. So what goes into that? And basically, again, remember, so this is the fractional Laplacian kind of, and this is function u multiplied by that potential, singular potential. Now, and when you see this, so this is a sort of convolution operator, if you like. So this is on a half line, so this is Wiener-Hopf, and this one has singularity 0. This is sort of fixed singularity, so you expect Mellin convolution to be somehow relevant, and this is exactly what happens. So this is basically the operator that I mentioned, although we subtract the value at 0. Turns out that you can write this operator as a composition of Caputo's fractional derivative and multiplicative convolution. And the multiplicative convolution is exactly squarely in the Mellin territory. And then you can, okay, I don't have time for this. So there are isomorphisms between those function spaces. So basically, I do order reduction to come to LP. And if you do this, you end up, so this is the operator. So you reduce this to this operator. So this is a Wiener-Hopf operator on half line. This is a different Wiener-Hopf operator on half line. And this is the Mellin operator. So here is Mellin transform. So you take the Mellin transform, multiply by B, and then take the inverse Mellin transform. So this is the operator. So you reduce everything to this operator, and this operator is, and actually it's quite painful. Sort of when you do compositions of pseudo-differential operator with Mellin convolutions, anyone who has done it knows this is really painful. I'm talking about non-zero order operators. So if you have, say, anyway, so you do this, and you end up with operator. And so what we do, so the Fredholm theory of this is covered by the work of my PhD supervisor. And so you can deduce Fredholm properties from there. But for us, it's not enough. We need to know invertibility, because eventually we want to do multidimensional case. This is a case like on the half line perpendicular to the boundary. And whatever is Fredholm here will involve arbitrary constants. When you go to n-dimensional case, those constants become functions depending on n-1 variable. And it's not Fredholm anymore. So you need to have invertibility here. And for p equals 2, so how it works, basically for p equals 2, you see that the operator is positive definite, so it has kernel 0. And then it's general theory that you, kind of Fredholm theory that you get it in LP setting. And so the Dudu-Chava theory, and I'm almost at the end. So the Dudu-Chava theory says that it's Fredholm if and only if this transcendental equation doesn't have any solutions. So see what you have here. You have this parameter alpha, that's the order. Tau, another parameter, is S minus 1 over p, so there's smoothness, that's integrability in the function space. So there's two parameters. And you have this variable r. So you have a transcendental equation depending on two parameters and a variable running through real line. And in Dudu-Chava's works, in any sort of works where you have singularities, Kondratiev, Pazia, Sasha, confirmed that you always have a transcendental equation and theorems. Everyone understands that. Theorems is stated in terms of solutions, unspecified solutions of a complicated transcendental equation. Everyone understands this. Well, Tony didn't. So what he did is he actually proved that this equation doesn't have solutions in this case. And the only case to cover was when psi is 0. And in that case, it comes to this equation. And this is the equation that I showed you. And it has one rule. Now, this is something that, an absolutely amazing thing. You imagine you have that equation. And you have two parameters. And basically, what you need to show is that this curve doesn't go through 0. So this one is a circle, it doesn't go through 0, but depending on the parameters, you have this. And look at different variations of parameters. So there's no obvious reason why it does not go through 0. So what Tony managed to do was he played with this experimental with MATLAB, and then he managed to identify regions of parameters for which he could, considering several cases separately, rigorously prove in God knows how, property of special functions, inequalities. It's like 10 pages. So rigorously prove there are no solutions. And in some regimes, two complex numbers are non-equal because they have different arguments. In some regimes, different moduli. So it's kind of absolutely amazing thing. So we haven't published this yet. When we publish, it will be basically, that will probably be the most impressive part of any of my papers, and I have nothing to do with it, absolutely nothing. So basically, the general theory comes from my mathematical father. The most brilliant part of it comes from my mathematical son, and all I can say is it happens all the time when talent skips a generation. So I kind of, I stop here. So this is graph of the root. There also Tony's work.
the set of parameters where the root exists.
No, the root exists always, but you see, this is basically. So what happens? That root will depend on alpha, the order, and it is always less than alpha, and it's just one. He proved it. That is one rule.
Okay.
And he has this calculation for the values. He rigorously proved that this is less than alpha, and then, and then he plotted the values. So it's just one root, and that's it, kind of almost explicit.
Nice.
With transcendental equation involving goodness, a gamma function, sines of complex argument, and two parameters. It's just, I don't know how he did it.